Good morning, evening, or afternoon, whatever the case might be. This video is going to try to put together the things that we've been doing and anticipate what we're going to be doing in the next day or two. I'll give you a big picture look, and then we'll give an example of how this works. There's going to be a lot of information we collect about these vector valued functions. And so it's important to understand how to know it, how to learn it. So first of all is the basic form. I'll use R for the function. We'll be given a function R of t. It's a vector valued function. This will be in three-dimensional space. I'll use an easy one here. T squared, t cubed. T is a real number. And so this is the first level. This is usually given to you, although occasionally you have to find such a thing. We don't actually graph these. We look at a trajectory. The trajectory will be in three-dimensional space, and the trajectory will be some curve. I won't necessarily draw this particular curve, but it will be some curve in three-dimensional space. This is the maybe I said graph, but this is the trajectory, this is the range. So what this function actually does is take the real line or a piece of the real line, and R maps it into three-dimensional space. This is the range of R that we're graphing, and typically this is called the trajectory. So this is the first function. There are a couple of derived functions. The first one is the derivative. So 1, 2t, 3t squared. And so it's important to know how to compute these, but the first derivative, the derivatives are computed in the same mechanism that one-dimensional ones are. They're just computed one component at a time. And these are given names. The first one is called the position. The second one is the velocity. And the third one is called acceleration. And they are given these names even if t doesn't represent time. T is any parameter. These words are used. So the first one that we want to talk a little bit about are, so these are the basic functions that we're going to be talking about. We're going to use these to derive other stuff, to analyze this curve and pieces of this curve geometrically and so on. And so there's sort of a second level. This is the first level. We're all done. We can find these. How do we use them? Well, first of all, this one here. The velocity, as any vector does, has two components. And here they have specific important meaning for us. There is the length of any vector, but the length here is called the speed. And it's given by a formula. It is the square root of 1 plus 4t squared plus 9t to the fourth. There is the speed function. And we're going to deal with these things as functions. We're going to find the speed at various points, but it's important that we understand that these functions are derived in order that we can apply to particular points and see what the speed is here or here or here. We can compute the speedometer reading of this position function as it traces out its trajectory. And then the direction. And the direction for us will be a unit vector t. So, and this again will be a function of time. So we can compute the unit tangent vector at any given time. And this will be the velocity divided by the speed. So 1 over the square root to t over the square root of the same thing and then 3t squared over the square root. I might point out that this function is algebraically far more complicated than the original because of the speed factor, and we've divided it out. But this is going to be important for us, and this is an important function for us. So all of these are functions that we will apply in various places to find various things. We'll also use the acceleration vector in ways that I haven't actually talked about yet, but we will use these. One of them is to find the so-called normal vector as a vector function, and I'll talk about these later. So this is new news, but it's new for next time maybe. So this is the basic setup. A position function is given, a vector valued function of one real variable. We are interested in its trajectory and the geometric nature of that trajectory. We compute the velocity and acceleration functions. From each of those, we can derive or find other functions. The speed, in this case, and the unit tangent. So what are the things that we're going to find with these? Well, I thought I might go ahead and find those. Those are kind of at a third level now. We'll talk over here a little bit and just make a list, and then I'll go ahead and do it. So one of the things that we find is tangent lines. At specific points. What is the tangent line at a specific point? And now we know how to find lines. We'll do it parametrically or in terms of functions. In order to find a parametric equation for a line, we'll need a point on it. Oh yes, that's given by this. And we'll need a direction. Okay, that's given by this, or specifically maybe this unit direction. So this information provides this information at specific points. So this is a particular thing that we'll want to find out. And the second thing we'll want to find out is the curvature at specific points. And this curvature has a formula as well. And it is, the definition of it is the derivative of the t function, not with respect to time, but with respect to distance. S represents distance. And this is an absolute value. This is a number. This is the derivative of t with respect to time divided by the speed, both of which we computed over here. Or we didn't compute this derivative. This would have to be computed. But this is what curvature is, and I'd like to talk about that just briefly, geometrically. Then I'll erase the board and talk about the new news. So let's erase this business. We'll just look at a graph. I'll put up a kind of a generic graph or a piece of a graph. And we'll take a particular point on that graph. So this is given by alpha of some, or r rather, of some particular point t naught. That gives that position. We know how to find the tangent line at that point. So that would be the tangent line. An important piece is how curvy this line is. And let me give the idea, and then I'll describe curvature in terms of that idea. If I put some little circles that contain this point on their boundary, sort of like a diamond on a ring, this circle is too small in the sense that if I put a bigger one here, that bigger circle also lies completely on one side of the curve. So these circles that I'm drawing all lie on one side of the curve. Some circles, though, are huge and lie completely outside the curve. So this circle here that I'm drawing lies completely outside. And there's exactly one circle which is kind of right in the middle. So anything bigger will lie partially on the outside. Anything smaller will lie on the inside. So too small, too small, too small, then you get too big, and there's exactly one circle in the middle. This is called a tangent circle. Now, all of these circles that I'm talking about are tangent to the tangent line. So they all have this as a common tangent, but there's one circle that has the property that it is the tangent circle, meaning that any smaller circle lies completely on one side of the graph, and at least locally, and any larger circle lies completely outside the graph. And that particular tangent circle has a radius. And this radius is a measure of this curvature. And the curvature we compute here, this computation, the length of t prime of s, this is called kappa, is the name of it, the Greek letter kappa, curvature, is equal to 1 over this radius. So this is actually a theorem that this computation gives this value. So, so the curvature is large when the radius is small, and that makes sense. If the radius is small, that means it's very tightly curved. So this is the geometry that we're interested in understanding or finding, this curvature or the radius or some measure of this curvature. And we're also interested in how to compute it. And this is our computation. And this is done point by point, but it's done via this function. So this is a function of time that you have to compute, or you could have Mathematica compute this for you. But this is the curvature function, and in order to compute it, you would have to have t-values. You plug those t-values in. It gives you a number for the curvature, and for the curvature, you can compute the tangent circle radius, and the radius of the tangent circle tells you how tightly that curve is curved at that point. These things are important. Maybe we'll take a look at the movie Hidden Figures. Hidden Figures, if you've seen it, it's a cool movie anyway. But Hidden Figures is exactly about this kind of thing. The computations that they do in Hidden Figures are actually somewhat accurate. They are accurate. And we can talk about the problems that they're dealing with on that big blackboard in the picture, but they are problems involving these trajectories. One of the big problems with it is computing this curvature. As you re-enter the Earth's atmosphere, if you re-enter too steeply, that is, if your curvature is too tight, too large, then your capsule burns up. If your curvature is too shallow, then the atmosphere is dense enough that you bounce off of it and back out into space. So there's only a tight window where the curvature is appropriate for re-entering the Earth, and it's one of the problems that they deal with. And to deal with it, they do these computations. So this is where we're at in the class right now. I've talked about how to compute this stuff, but I want you to think about computing in a hierarchy. First, the three major vector valued functions: position function, velocity, acceleration. And then specifically from velocity, we get the formula for t. And then we also get the speed. And then using those, we can go ahead and compute a third layer that tells us something else, in this case, just one other thing so far, and that's curvature. Now, I'm going to erase all this and talk about a little bit of the new news. What else we're going to compute. And it is this. When you have a curve like this, at any given point, we have this t unit vector, a unit vector pointing in the direction, in the tangential direction. Actually, the direction of travel is this way. But if we look at the acceleration, r double prime of t, we get a different vector. So this is r double prime of t. And some of the acceleration is in the forward direction here. And I'll just extend this a little bit. And you can determine how much of the acceleration is in this direction by projecting onto here. So let's see, I'll put this in green. And this green vector, the projection of acceleration onto t, is called the tangential acceleration. And there's other acceleration that is non-tangential. You can see it here. Some is in this direction, but the other component is perpendicular to tangential, and this is called a normal acceleration. And if you take the relationship between these is that if you look at the tangential acceleration, and add it to the normal acceleration, you get the acceleration. So tangential acceleration is a projection onto t. That's what the acceleration, the tangential part of the tangential acceleration means. So once you get that, you already have acceleration. You can subtract those two to get the normal acceleration. So this is the next step that we're going to look at, is compute these two. And in order to do that effectively, we have to know how to project one vector onto another. That was part of the homework I assigned on Friday. If you haven't done it, please do it by Wednesday. I'd like to know how to do this, not just for these vectors, which are complicated because they've got t's in them, but any vectors. Project a given vector u onto another given vector v. Just how do you do this? How do you project one vector onto another? If we had the length of it, if we had the length of this green, that would be enough, because we could take this length and multiply by t, and that would give a vector in the direction of t, so in the tangential direction, with the proper length. So finding the projected vector that that's the green vector we actually want, it is, all we have to do is just find its length and then multiply by the vector t. That's enough for today, I think. On Wednesday, we're actually going to work with some of this stuff, and then the video for Friday will actually compute these vectors and one other one. And we'll look at some cool stuff. Associated with this, there's a little Mathematica page with computations for all this, so take a look at that too. You might want to record that or copy it down and put it in a directory where you can find it easily. Thanks a lot. See you Wednesday. Have a good couple days, but not too good.